Good afternoon, everyone. Thank you for joining this session. My name is Sandor Dargo, and we are going to talk about undefined behavior in the STL. Just to make sure that you are where you want to be, right here at the CppOnSea right now, there are two parallel sessions about the STL. And while Danila's presentation is clearly about performance, here we are going to speak about how the code behaves, about different contracts that the STL implies but doesn't, or maybe better to say can't enforce. So the three main goals of this presentation is to explain different observable behaviors in C++, show manifestations of undefined behavior in the STL, and to briefly discuss what we can do against them. But before jumping into the deep C++, let me introduce myself briefly. My name is Sandor Dargo, and after a few years of database administration, I joined Amadeus exactly 7 years and 1 day ago to pursue my dream and become a software developer. It was really difficult in the beginning. Well, you all know that, but I had some wonderful colleagues, and since then I really think that one of the most important things that we should do is, besides, of course, writing production code, and we should share knowledge. So that's why I'm here, and that's why I write my blog mostly about coding C++ and a bit about the books I read, or how you can apply Stoic philosophy to your job as a developer. And with my two little very active kids, we like traveling, not so much these days. And we try to experiment a lot with sourdough baking, something that we really find satisfying. But that's more than enough about me. Let's have a look at the agenda. So first, we are going to speak about the vocabulary, just to make sure that we mean the very same things by certain terms. And then we are going to see the different reasons of why undefined behavior exists, especially in the STL. Then we'll see quite a few examples for it. And then at the end, we'll see the countermeasures, the possible countermeasures that we can take. So before we jump into the implied contracts of the STL, let's clarify the meaning of these couple of terms, just to make sure that we are on the same page. So you might know who is this guy. I give you a hint. Yesterday at the keynote, Walter quoted him. He's Alexander Stefanov, the guy who said that the fact that you can describe reality in terms of numbers was probably the most fundamental breakthrough ever. Well, this guy, Alexander Stefanov, he had a dream. He wanted to create a generic programming library with the idea of abstracting from concrete, efficient algorithms to obtain generic ones, so that we can combine them with various different data structures to solve problems in our softwares. Well, in a much easier way than we would do otherwise. And he had this already in mind in the 70s, but he had no language support. Well, if you read some articles, books about or from him, then you will see they even tried to build their own language for it, but it was not adopted in the industry. It was only used at the universities. But then in the 80s, he tried to implement his idea in Ada. But again, it was a language that was not widely adopted and never got widely adopted, only in the defense industry. And he started to think more and more about using C++, but back in the time it was a bit more difficult. It didn't have so many features, mostly about templating than today. So he had to wait a bit. And then in 1993, a former colleague of his convinced him to, well, to present his idea, present his work in progress to the C++ committee, which he made in November 93. And from now on, it starts to really fast up. In just a few months, in March, he submitted the formal proposal. And just, again, a few months passed, and he got the final approval of the committee. And in the next month, August, HP released the first implementation. We released it for free. They wanted, fast and wide adoption in the industry, which we all know it happened. So if you just think about how fast this moved, and now you think about, okay, how much time does it take to accept an idea, to implement an idea? If you just think back about what Nico said this morning, well, this was something really important, and this convinced almost everyone that, okay, we need this, we want this. So there we had the STL. But what is the STL? What's included in it? Because in fact, there is no such library as the STL. But if you tell a C++ programmer what's the STL, most probably they will still think about mostly similar things. Because it's, after all, it's a set of template classes and different functions that, they provide solutions for, well, common problems, and through generic and template programming that was mentioned before. So what do we have in it? We have a lot of algorithms. You have containers, and the algorithms, do they work on the containers? Not really. We'll see. We'll see this. You have function objects like stud greater or stud logical and a lot of others, so that you can, let's say, fine-tune your algorithms. And then you have the iterators. In fact, these algorithms work with the iterators, work through the iterators on the containers. They don't work directly on the containers, and this has really serious consequences, to say it like that. So that's what is included in the STL. But then the next the next terms we want to discuss is like, what is the behavior of the code we write? Or we could ask another question. Does the standard describe the properties of your program? There are a lot of different behaviors. You can see some now on the left side that we are not going to talk about today. Don't have the time for this. But we are going to talk about unspecified behavior, implementation-defined behavior, and undefined behavior. So let's start first with the unspecified one. Well, what is unspecified behavior? Rules are not specified by the standard, no surprise here. And even the implementation, the compiler doesn't have to document it. And in the end, completely different results are valid. So your code can produce completely different output, and it will still be valid. The good news is that the consequences are strictly limited to the lines where you use unspecified behavior. So let's see two examples. Like if I can get my pointer. So here, for example, if you try to compare the address of two variables, that's completely unspecified. You shouldn't rely on it. Well, if you know your compiler, you know your platform well, you can guess. You might know it, but you should not depend on it. And another example for unspecified behavior is the the expression evaluation order. Now, this is something that changed a lot recently, mostly with C++ 17. And some things that were undefined became unspecified, some unspecified become specified, but still expression evaluation order is something that that is kind on behavior. We see here an unspecified one. So here on line 37, you see that we have this add function, and we pass in two parameters, left and right. Well, in fact, they are both function calls. So what are they? What do these functions do? Left will assign 100 to a global variable and just return it. The other one, right, will also use the same global variable, increment it, and return the result. So obviously, here it really matters which function call will be evaluated first, left or right, left or right. Well, it's unspecified. Well, I used GCC here, and I got the result 434, which means that first right was evaluated. It incremented x to 334, and then added 100 from left. But if I try the same code on Clang, I got the other results. So that's what unspecified behavior means. Now let's move to implementation-defined behavior. It's really like unspecified behavior in terms of the consequences, let's say, are strictly limited. But here the implementation must document the result. So if you want to think about some examples, you can take the default integer types, or even the number of bits in a byte. Or if we think outside of C++, why not? Let's think about the databases. The behavior of ordered by on null values is implementation defined. So for example, MySQL will consider nulls as lower values than all the others, while the other implementations, like Oracle, for example, it will consider it as higher. So in MySQL, null will come first when you order by ascending, while on most of the other implementations, we'll put null values at the end. But again, it's well documented, something that you can know. Still, probably it's better not to depend on such behavior, well, if you consider portability an important issue for yourself. And then here we are, undefined behavior. Here we break the rules completely, and the compiler owes us nothing. In fact, there are no requirements on the behavior. Maybe your whole application will crash. Maybe you just get some logically impossible results. Well, the behavior is quite non-deterministic, and honestly, the compiler can remove completely some execution path. So if you want to see some great examples, something that's really food for thought, I would suggest to watch the talk by Michael Spencer called My Little Optimizer, Undefined Behavior is Magic. He presented it in CppOnSea 2016, and well, he has a lot of examples for really quirky C++ behaviors. Well, here now I just share two really simple examples. So if you access uninitialized variables, you have undefined behavior, or if you want to delete some objects, derived objects through base class pointer where there is no virtual destructor, that's also undefined behavior. Now, I don't bring you more examples because we're going to see quite a few. So why does undefined behavior exist? Well, what is C++? Well, we can still say that okay, it's a superset of C, even though okay, in some cases it works really differently, but we have a heritage of C, and there portability was something really important, because after all, and I borrow some words from the book Code, the Hidden Language. C, after all, is just a high-level assembler that has to work well everywhere. And from language designer point of view, well, undefined behavior was a way to cope with significant differences between compilers and different platforms. And sometimes it was just historical. It was easier to say that, okay, on one platform it was considered like this, on the other it was implemented like that. We, the committee, we don't want to say anything about this. Well, it's undefined. You go as you wish. And it gives some other freedom for the compiler writers. You can optimize a bit more the performance, or you can shorten, of course, the code, but we'll see. And this is not a good reason, I think, for undefined behavior. But you can have some shorter APIs. We'll see how is that. And after all, yeah, you can have simpler implementations in your compiler. It really depends on what you want to focus on in your implementation. And why does this exist? Why does undefined behavior is allowed in the STL? Well, it was not very easy to find the answers for this. So if you find better reasons, you can, if you know about better reasons, you are free to post it in the Q&A. I will read it in. Well, one is efficiency, because after all, you should pay for what you use or what you want to use. We'll see an example. We'll see quite a few examples for this. You can have a shorter API, but this is going to be less and less important, especially with C++ 20 and the ranges library. And of course, the implementation freedom for the different implementations. Well, it's important. So now let's have a look at the different categories, let's say, for undefined behavior in the STL. These are arbitrary categories. I was looking for the undefined behaviors that are there in the standard template library, and I categorized them like this. So there are 4 categories here. When we are pointing beyond the limits of a container. Second one, when we use inconsistent iterators, we'll see what are they. When you have unsorted data, when you use unsorted data with certain algorithms, and there are the others that I didn't or couldn't classify. So first, let's talk about some cases of undefined behavior where we go beyond the limits of one single range, one single container. Why do I say one single container? You will understand it in a few minutes in the subsequent section, in the second section. So probably this is the most basic example for undefined behavior in the STL. The offset operator versus the add function, the add method. Well, first, what's the very, very important concept in C++? That you pay for what you use. And with the offset operator, you have no bounds checks, meaning that, let's say you have an array of, or standard array or a vector of 5 elements, and then you call the offset operator with, I don't know, 42. You will have no exceptions. There are no bounds checks at all. You don't pay for it. On the other hand, what can go wrong? Well, anything. On the other hand, if you use the at, there's always a bound checks. And it's something really interesting because there are not a lot of exceptions in the STL. In fact, apart from some memory allocation exceptions, I couldn't find be anything else than this bounds out of or out of bounds exception that is thrown by the at. So it's something say really special, and it can have serious performance overhead. So what you can see on the right side is the quicksort algorithm evaluated by QuickBench. And here on the top, okay, I didn't use any optimization. And here with green, with the lower value, you have the version where the offset operator is used. And here we used at. Otherwise, it's the same quicksort. The difference is about 250%. They both have the same complexity. It doesn't change. Of course, they have the same complexity, but the live runtime performance is really different. And then if you turn on some optimizations, here I think I used O2, then the results are pretty much the same. Even the compiler could optimize a bit more the quicksort with the at method, but it's not so important, the difference. And well, you shouldn't really rely only on your optimizations in the code. So you should choose what you need. And the consensus is that at is rarely needed, because most of the time, how will you use offset operator or at? Well, you would use in a loop, in a row loop, and there it's pretty much evident that you will not go out of bounds. Well, unless you have some concurrency issues, or you invalidated your iterators for other reasons that we are actually going to see in a few slides. So I think this next one is probably the most boring slide in the whole deck, but I still felt important that I share this with you. So if you have an empty container and you just try to call any of these, like back, front, pop back, pop front, you have undefined behavior. You can have different outcomes. I managed to provoke segmentation for double free, or just to get random values. If you want to play with these examples, you will find some Coliru links in the presentation once it will be available in the presenter's notes. Okay. So I mentioned the iterators, that they might get invalidated. And an important thing to keep in mind that, well, you shouldn't modify a container while you're iterating over it, because iterators, they have a certain validity. They have a lifetime. And there are certain calls that will invalidate their positions, the iterators' positions. And for example, erase is one like that, but if you think about inserting elements in a loop, well, you should also check if you provoke some undefined behavior there. So here in the example, what do? We have a vector with a few numbers in it. Then we are looking for the value 4. And if we find it, we erase it. Well, if you saw certain talks from Herb Sutter, for example, who is our keynote speaker tomorrow, he would say that, okay, you should never use row loops like that, because you have a big range of algorithms in the standard library, and they are safer to use because, well, they won't lead to such errors, and he's perfectly right. But many times still, if we look into production code, unfortunately, we'll see such examples. Why? Well, good question. I don't want to answer, but most probably it's a lack of knowledge sharing. So what can happen here with this undefined behavior? Maybe you will see nothing observable. It really depends, well, on the implementation and in fact on the data that you are passing in. But by nothing observable, we can also mean that, well, actually there is something wrong, but you are just not able to see it because, well, in this example, we have some hard-coded values, but obviously in real life, most probably this will be something something dynamic, and you would just not notice if something is not removed, whereas it should be removed. But it might be that you notice it and you see the unexpected results that, for example, some values are not removed. So, for example, if I modify this vector and I put 2 4s one after the other, only one will be removed. Well, of course, again, it depends on the compiler you use. But when I was using GCC through Coliru, well, only 1 4 was removed because we jumped through the other. But if you have this 4 in the end, it's very likely that you will get the segmentation fault and the core dump. Honestly, probably this is still better than unexpected results. You have a better chance to actually look into the code and find this erroneous usage of erase. So now let's look into the inconsistent iterators. It's cases when we fall between the cracks. We fall between, in fact, 2 ranges, and we just mess up everything. But why is that? How can it be? So let's take, for example, the signature of transform, of the transform algorithm. So what can we see here? That we'll pass in an input range defined by both the beginning and the end iterators. And then you might pass in a second range, but there you don't define the end, you only define the beginning. And as we said, we don't pass in containers, we pass in iterators. And this is the same for the output. You only define the first element, the beginning, okay? And this, well, this spares us like 2 extra variables that we would pass in here at the end and probably for the output as well, though there it's really debatable because you can add inserter, and most probably you will add some inserter iterators like the back inserter. But this brevity has consequences on undefined behavior. Many things in many combinations can go wrong. So let's see a few of them. Because, well, algorithms, they don't validate ranges. In fact, you might combine them. What do I mean by combine? So here we declare 2 containers. What's the type, by the way? What's the type of this? Okay, here we don't have a vector, we have a standard initializer list. We declare another one with some really bad names, which we do frequently, unfortunately, in real life, that we don't use descriptive enough variable names. Funny thing is that at the same time, Kate is speaking about naming things better. And let's say by by an accident, you pass in the beginning of the first iterator and the end of the second one. Well, I assume that it was not meant, but maybe you meant it because you saw this example and okay, I can combine ranges. In fact, I want to copy from both the odd numbers, and what you get is 1, 3, 3, 5. Is it the correct result? Well, the result is correct, but you shouldn't trust it, because here we depend on undefined behavior. Algorithms like CppOnSea will not validate that these two iterators they are related to the same container. In fact, it doesn't even have the means to do it. And if we alter a bit our example, so for example, we change the type from the standard initializer list to just to vector, then we'll see something strange. In the middle, you have 33. What's that? And in fact, if you play with this example and you would just copy all the numbers, you would see a lot of zeros. Well, that are not odd numbers, so here they are not included. What's going on here? Well, I said algorithms, they don't validate ranges, and you can get some really strange results. We'll see soon why exactly. So with list, I got some execution expired. I got a timeout. We can say the good news is that at least the types you cannot combine, because as we said, these algorithms, they cannot validate if two iterators are related, are pointing at the same container, but they can check the types. And here it sees that, okay, this one is an iterator on a vector, and numbers 22.end is an iterator on a list. And there is no matching function call for that. So at least there, you don't have undefined behavior, you have compiler protection. And you can also not combine, let's say, the value type of these containers. So even an integer with an unsigned integer, it cannot be accidentally combined. Just say good news. Well, there is a way. There's always a way. You can inject a different value type, a different contained type in the middle. Like you see here, you have numbers 21, numbers 22, some bad names. I even mispronounced it. And for some reason here, you have a different vector with some floating point numbers in it. And then you see even stranger results. And from where does this huge number comes from? Well, it's one of these two floating point numbers, because what happens is that CppOnSea, if it expects integers, and well, what do you have in the memory? Well, just zeros and ones. So it will take a bunch of zeros and ones there, and it will interpret it as an integer. So even though here you had a float, well, you just copied an integer. And you can even inject a different container type, but this is really just for, let's say, for the example. And a different type of problem with for example, transform that we saw in the beginning of this section is that when you have two different input ranges, and what is expected by transform, what is implied by the contract, is that the two input ranges, they have the same size. But because the first range is passed in by two iterators, beginning and end, and the second one is only passed in by the begin iterator, it can't check anything. It can't check that the second range contains at least as many elements as the first one. It's your job as a user, this API, as a caller, to make sure that you pass in enough values. In fact, you might think that, well, if I want to combine, like I want to zip these two vectors, when I don't have a value, it will just take 0. And it might happen. Well, it's undefined what will happen, but as you see, we had some strange results. So it's not that, okay, to 1 we could add 10, to 3 we could add 30, to 4 we added 0, for 5 it also worked, even for 6, but for 7, no. We added that 33 that we saw before in our first examples. And then to 9, we just added a huge number. Well, we'll see soon what is really going on under the hood. And well, if you want to just play around, it's really easy to provoke core dump segmentation fault. I just wrapped everything into an I struct, well, just a struct, and I declared everything on the heap, and we had directly a segmentation fault when we had no value. So what's going on? So how most of these containers are built is that you will create a variable on the stack, and you have the overhead on the stack, but the data, okay, it will be on the heap. So you see that, okay, when we have a vector, okay, we have a contiguous memory for it. You have the 0th element, and the next one, the next one, the next one. After the n, which is pointed by the here, the end, you might have some, let's say, empty spaces, and then you have the end capacity. So what happens is that in these algorithms, the iterators are just advanced by 1. So from one integer, you move to the next, you move to the next, you move to the next, you move to the next. And well, there might be nothing there. So just take 0. There might be, in fact, anything there. Sometimes it will be just the next container. Sometimes we go to really uncharted territories, but what we could see in our previous examples is that, well, we just went to the next container. In fact, we took some zeros between the last element and the end capacity. There was some padding with the 33, and then we started with the other vector, and we went until we reached the end of the second vector that we actually passed in. Now, this is something interesting, and if you change, for example, your compiler, then these examples will not going to work. They are not going to produce the same result, because let me go back a few slides. So why not here? So when I use GCC, after numbers 21, after this vector, you had directly the data of numbers 22. So the example worked well with this, let's say, padding, taking the 33 that was in between. But when I try to run the same example on Clang, there it works the other way around. Then there, okay, you declare still in this order, numbers 21, numbers 22, but numbers 22 will have, well, it had lower addresses than the numbers 21, which means that your iterator is always advanced by one, by one, by one, but you will actually never reach the end of number 22. So either have a segmentation fault or a timeout, depends. So that's what's happening under the hood. And the takeaway here is that, well, the algorithms, they don't validate ranges. And there are no explicit error messages unless you mix also the types. But if you don't mix the types, you just use, for example, bad variable names, then you're on your own. You might get some runtime error or strange results, compilation error only if you mixed the types. But, okay, you really have to double check what you pass in. And using good coding guidelines or using good naming and coding guidelines, something that I will talk about the lightning talks this evening, is something that really can help you to avoid such problems. Or if you use the ranges library, where you don't have to pass in these pairs of iterators, but you work directly on a container, not through iterators. Now let's move to the next section, which is about algorithms that require that the data that you pass in is already sorted. Well, I know this might sound straightforward, but without explicit checks and explicit contracts, it's better to remind ourselves. So let's take, for example, binary search. Here we take by the usual pair of iterators, this numbers vector, and we are looking for the position of number 7. You call binary search, and what we see is that, well, it's the very first item at position 0. Well, of course we see it's not. Well, you might not see it in real life until a customer complains that I don't know, they can't board their plane. I'm working in the travel industry. That's why the example. So then, if you sort it, you'll find, okay, 7 goes right after 1, so it's in position 1. Good. So again, you have to repeat that C++ is a language where it's really important that you pay for what you use. And that you want to use binary search, well, it implies that you already pass in something sorted. It would be expensive to run some sortedness checks at each call of binary search. You have to remind yourself that algorithms, they come with their own contracts. And even though they compile or they might seem to work, it's better to check what exactly is in their documentation if you are unsure. Because unless you might get some undefined behavior, you might get something much worse than just finding a bad position. But in fact, okay, it really depends what is worse, to find something in a bad position or to have some strange runtime error. Probably the second is better in the long term. There are some other algorithms like that that require that you pass in your container sorted. Lower and upper bound are algorithms like that, which for, okay, the binary search, even just by reading the name, it was straightforward that, okay, I should pass in something sorted. Here, maybe it's not so evident, because you could expect that if you have this 188, 54, 7, blah, 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 777, here a 7 again, and you look for lower bound 7, it should return this. And the upper bound, maybe it should return that. Well, it's not the case. It works on sorted ranges, and if you have like multiple 7s, obviously they will be next to each other, and lower bound will find, well, it will return you the position of the first one, and upper bound will return you the position of the last one. And there is one more like that I want to mention, is the merge. Well, merge will most probably work, and it will give you a result that you might argue that it makes kind of sense if you just, well, if you are not sure what to expect. You want to combine these odd numbers with these even numbers, and you look in the beginning, it starts with 1, 2. Okay. It's not great, but you might think it's okay. It expects sorted containers and it will work fine. But if there is another example that, let's say it gives you a stranger result. Here again, you have some odd numbers and even numbers, and then you have 2, 10, 4, 8, 6. Good. So you got first one. First, you got the even numbers because you used this stud creator functor here to make sure that you take the bigger value. And then you had the odd numbers because it started with the smaller number. So you try to merge with the stud creator, and first you got all the numbers from the vector that starts with the greater number. You actually you can argue that, okay, I wanted this, but no, you read the contract, you see what it does, and you see what it expects. And we should always read, okay, but in what cases will my behavior be undefined? And this is like that. Okay, to merge, you have to pass in sorted numbers. As soon as you uncomment these lines and you run again, you will have the numbers and the merge numbers from 1 to 10 in order. Let's move on to the last section before we wrap up and see what we can do. I mentioned two topics here, unordered maps and splice. Both hold something interesting for us. So when you are splicing, pay attention. What does splice do? So if you call on this list splice, it will take numbers from, take items from another list and insert those items from where you call it. So in this very example, it will be undefined because you want to insert what do you want to insert here? In fact, you want to insert in the beginning of odds numbers, items from the evens list, but you actually pass in the beginning and the ending iterator of odds odds, which we use here. Now this is going to be undefined because these two, they should define a range in this second parameter. But again, as we said, there is when we are working with iterators, well, the standard library will not help you with any checks if certain iterators belong to certain containers. So here you just got, well, in this implementation, timeout. In this other example, what did we do? We invalidated this iterator. So this is, I would say, the splice, this is the simplest signature of splice. You call it on a list, you pass it an iterator that you want to insert elements at that position from this other list. And it means that, okay, we defined our iterator with the beginning of the odd numbers, and we want to just insert all the even numbers in the beginning, well, before the odd ones. But in between, we invalidated the iterator by popping the first element, and that provoked the segmentation fault. So if you're working with such functions, such algorithms like, for example, splice, that is like a lot of relative rules, you can say, or a lot of different input parameters from different containers and ranges, pay attention and be prepared for a bug. It's better to test it or even wrap it before you commit. The other interesting thing is other undefined behavior. In fact, the last ones that I want to show is related to unordered maps. They also come with their undefined behavior. So there is this function bucket, and you can pass in a key, and it will return the index of the bucket where that key would go. And the return value is undefined if you have no buckets. But the good news is that in practice, it doesn't happen much because unordered maps are initialized with some size. But in fact, that's not something required. In theory, this might happen, this undefined behavior. And another undefined behavior related to unordered maps is bucket size. So it will return you the number of the elements in the bucket with a given index, but it works like operator add. If the index that you pass in is not valid, the effect is undefined. There are no runtime checks. You're on your own. As said, you pay for what you use. So, what can we do? During the last 54 minutes, we've seen a lot of examples for undefined behavior in the STL. We know about them. We pretty much understand them. But what can we do about them? What shall we do? Well, should we use try-catch blocks? Well, obviously no, because as we saw there, well, we didn't see any exceptions. We mentioned one with the add function, but otherwise, if your memory allocation goes well, you have no exceptions, definitely not on these. Should we add some explicit checks? Not really, because you cannot protect against typos that we had that we passed in accidentally, of course. Iterators that belong to different containers. We cannot really protect ourselves with explicit checks. We can protect ourselves in different ways against that. Should we re-implement maybe the STL? Well, sometimes maybe that's an option. There are certain use cases, certain requirements that that might make you so. For example, you have the EASTL for mostly for the gaming industry for their requirements, but probably this is not the way you want to go. I think that the good solution is that you automate what you can and knowledge sharing, education. So it's always good to listen to your compiler. Turn on whatever warnings you can and treat them as errors. Most probably, you will find a lot of, well, undefined behavior, a lot of bugs, just like Matt Godwell said yesterday in his talk. You can use some sanitizers that are available for, well, for major compilers. And I think there will be a talk about that maybe tomorrow. And you should follow good coding and naming guidelines as well, because they will seriously limit the possibility to err with in such ways that that we did. And well, we all know the coders that that they say, okay, it works. I don't understand why it works, so I ship it. I was there myself as well. I didn't care as long as it works. And then through, well, so say the hard way, I started to wear you more the concepts that are behind to understand what is going on. That's really important, because when you understand the contracts, the implied contracts given by certain APIs, then you can work much better in an easier way with them. And what is really important, that we share the knowledge if we got some new. We can schedule knowledge sharing sessions in our teams. We have an hour dedicated for that in our department every week. And we should also do code reviews, like serious code reviews, something that we had a talk about yesterday. So, as conclusion to say, just to recap, the STL is full of undefined behavior, by design. But if you respect the contracts, if you respect what is written in the documentation, you will not run into them. You will not get bogged down because of the examples I mentioned. And here, automation and education is key in this. Again, use your compiler, use sanitizers, and share the knowledge. And just to remember, well, for the compiler, you, as a programmer, you are God, and God cannot err. So if the compiler sees some error there, then it will think that, okay, I have to eradicate this because it can't happen. It shouldn't be there. So it might remove, again, complete execution pass just because it can do anything. It tries to protect you, the coder, from introducing defined behavior, erroneous code. So Thanks a lot for attending the presentation. I'm going to check the Q&A if there are any questions. So is erase if safe? Then erase, remove. You might meant that is erase if safer than erase remove idiom. But again, what I would propose here, well, erase remove idiom is something powerful, and it will work. Is erase if safer? You have to check for your use case again. Check for the documentation to make sure that you have no undefined behavior there and what is the intended usage. It depends also on the container type that you are using. There can be differences based on the container type, and it's always good to check the documentation if you are unsure. C++.com, cppreference.com, they are quite good on this. You will find almost all the references to undefined behavior. If there is no other question, then thanks again for listening, and see you around.